Here we're going to look at specific examples of taking the partial derivative of a voltage function to generate the electric field equation. So to do this, we are going to utilize the equation that the electric field equals negative the gradient of the voltage. Now for us, that is going to be negative the partial derivative with respect to x, y, and z, but I'll leave it as with respect to r, leave it very generic, of the voltage. So the way that plays out for us is that we are going to take the partial derivative of the voltage, first with respect to x only. And that will be the first term. All right, so let's take the partial derivative together of this voltage expression with respect to x only. So that means anything else, the y's and the z's, remain as constants. So they stay in there, but they remain as constants. So the derivative of 3xy squared, if y squared remains constant, then the derivative of 3xy squared with respect to x is just 3y squared. Now, the derivative of 4z squared with respect to x is 0, so we get nothing. The derivative of 27x squared yz, y and z are constant, 2 times 27 is 54, the negative stays. 54, derivative decrease, so the x squared becomes an x, y, z. So that gives us the first term. We put the x hat with it, and we will do the same with the voltage in the, oh, my y's, and I keep writing x's. Let's correct that. That should, of course, be a y, and that, of course, is a z, so make those changes, please. Take the derivative of the voltage with respect to y, the derivative of voltage with respect to z, put y hat, z hats there, make sure we have our negative out front, and we get the right answer. So pause the video, give that a try, and then unpause it, and we will see if our answers agree. Okay, hopefully you have given it an attempt, and let's see if we get the same answers. So again, let me make those changes quickly here, that this is a y and this is a z. But the derivative of the voltage with respect to y, now in this case, x and z become constants. So 2 times 3 is 6, derivative decrease, 6xy. There's no y here, so we lose that term at 0. And here we have the derivative of negative 27 x squared yz with respect to y. So that gives us the negative 27 x squared z, and we put that with the y hat. We do the same thing with the z. So for this case, let me erase this. For the final case, we get that the z is the only thing we are taking the derivative with respect to. So that means y and x are constants, z stays, y and x are constants. So now we lose that first term, that doesn't matter. We get 8z, and we take the derivative of negative 27 x squared y, z with respect to z, so that gives us the negative 27 x squared y. We put the z hat in. We make sure we have our negative out front, and we are done. So that is it. We just leave that as our answer for the electric field. And of course, make sure that you have in here explicitly that you're only taking the derivative with respect to each variable and holding the others constant. So again, you can attempt to do the same thing we just did with this voltage equation down here. Pause the video, and when you unpause it, I will show you the solution. Okay, hopefully you have given that an attempt, and do our answers agree? So with respect to x, right, with respect to x, the y's and z's are constants, so we get the 12 x squared z squared. We lose the middle term, and we are left with 20x cubed z for the x set. I will leave it to you to confirm that your y's and your z here are correct. Hopefully you see how the game is played. Of course, if you have questions, I would be more than happy to go over this again in class. You are absolutely responsible for being able to take these types of derivatives.